Right, welcome back everyone. We're very happy that Christophe Garban is going to give us the first instalment of the last mini course on the BKT phase transition. How are people finding the temperature now? Is it too cold now?
It's cold.
Yeah. It's too cold. Everyone's too cold. Okay, so we turn off the air conditioning.
Maybe we can put it.
Oh, we can ask them to turn down the air conditioning. Ah. Yes.
You're not used.
We can even try and do it ourselves.
Problem solved.
Okay, very good. Take it away, Chris.
Okay, so thank you very much for the invitation. So in this mini course, I want to tell you about spin systems which live in a target space which is continuous. Most of the course will be about the unit circle S1, but I will make some diversions away from the unit circle from time to time. And most of the course will be about the Berezinskii-Kosterlitz-Thouless transition. But at least today I want to make an introduction about what those continuous spin systems are, what's the definition, what are the different possible phenomena. And I like things to be lively, so if you ask many questions and I tell you a third of what I planned, I'm very happy. So don't hesitate. I wanted to do it all blackboard, but given the way the room is built, at least half of this day this will be on slide. And next time, I think Thursday, it will be on blackboard. So the first slide, I will stay some time on this one. It's about the definition of spin systems on ZD. I believe you've seen the Ising model a little bit in Maurice's talk just before I arrived, in the five first minutes maybe. And in Malin's lecture also yesterday. So in this lecture, I will have a lattice, which will be ZD. In most of the course, the dimension D will be set to be equal to 2, so we'll have the two-dimensional grid. And each vertex of ZD will carry a spin, which, depending on the model, will live in different possible target spaces. So, for example, the Ising model, each vertex of ZD will carry a spin which will live in a very small set, which will be either +1 or -1. This model, which is called the XY model, each vertex of Z2 or ZD carries a spin with values in the unit circle S1. And this one is called the classical Heisenberg model. Each vertex carries a spin in the two-sphere S2. And of course, you may continue the list forever if you have values in the sphere Sn-1. This carries the name of the spin ON model. So maybe I can add this information here. If sigma goes from ZD to the sphere Sn-1, it's called the spin ON model for the simple reason that the symmetry group of this spin system will be the ON group. And so those are called spin ON model. So with this general definition, n equals 1, which is the S0 sphere, which is a little bit degenerate. This is the Ising model. N equals 2 is called the XY. N equals 3 is called the classical Heisenberg. And n equals 4, as far as I know, does not have a proper name. It's the spin O4 model and so on. So what do we do with so this is the state space of the model. I still need to equip this state space with a probability measure. And the way to do this is to assign to each such configuration a weight, a Boltzmann weight, which will favor some configurations versus others. So to make everything rigorous, if you've never seen this before, You cannot do it right away on the full ZD lattice, it's too big. But what people do, they take finite boxes lambda inside ZD. So typically they will take, sorry, my voice is a bit against me today. So you take a finite box which we usually call lambda, and if there is a subscript lambda n, this is meant as the n by n box, or 2n by n box inside ZD. And once you have a finite box inside ZD, this Boltzmann term is well defined for each spin configuration on this finite box. And then this probability measure is well defined. So maybe I will, how should I do, so that this remains visible. So let's even switch. Okay, I will try this. Display off.
Normally, if you just say you want it off, someone will magically turn it on.
Because they are.
But maybe this is dangerous. If I write here, is it visible enough? Or? Okay, good. So, if I pick this finite box lambda in ZD, and I take sigma a spin configuration, so maybe let me do it, for example, the case of the XY model. So sigma will be S1 to the power lambda. Each point in lambda will carry a value in S1. I want to define a probability measure which depends on beta, and beta is called the inverse temperature and corresponds to 1 over a temperature T. And I will often insist on beta versus T because I always get confused. So please check I don't do it the other way around. And I want to assign a weight to this sigma. So, okay, I changed my mind. I start with Ising, and then I will make xy because there is one little subtlety. So this is a finite set, and thanks to this, I can define a weight for each element in this finite set. When I will go to the xy, it will not be way more complicated, but I will need to write a Radon-Nikodym derivative. So to start with, I want to start with Ising. And I want to set a weight here, which is going to be exponential beta times the sum over the nearest neighbor edges of sigma I times sigma j. If I do this, this is not a probability measure, because when I will sum over all sigma in my state space, I will not get 1. So every time in this lecture, when I write this, the weight of this is proportional to this. What I will mean is that I want to set the probability of this spin configuration to be defined as 1 over a partition function, which depends on the box and the inverse temperature, times exponential beta sum over I next to j, sigma I, sigma j. Well, this is called the partition function and is defined as the sum over the whole state space. So all the points in this hypercube of dimension, the number of vertices in my box, exponential beta sum over I labeling j, sigma I, sigma j. So if I do this, this defines a well-defined probability measure on my state space. I will make another tiny comment about it. Which is a very classical thing in statistical physics, but it's good to know. I could define it a little bit differently by setting this weight to be proportional to exponential minus beta over 2 times sum over I next to j, sigma I minus sigma j squared. If I do this, it turns out that this is defined as 1 over z tilde exponential minus beta over 2 sum over I next to j sigma I minus sigma j squared. And it gives exactly the same measure as before. The partition function is different. This weight is slightly different, but it gives exactly the same model. So that's the Ising model. I will go back to the slides to show a few pictures and how the model behaves as a function of beta. But when we do this, it's perfectly well defined for lambda, a finite box in ZD. And then one of the games of statistical physics is to let lambda grow so that it spans the whole lattice ZD, and then to wonder how the measure on the full lattice behaves as the function of beta. Is there a phase transition, and what's going on, and so on. So this step is not too difficult in the case of the Ising model, but for example, it's completely unknown in the case of the S2 valued spin system. So what people usually do to prove that there is a limiting measure, they need correlation inequalities and tools like that, and they are not always easy to prove when the symmetry group is more and more complicated. What is very easy to show is that you have subsequential limits. The reason being that -1 plus 1 is compact. Okay, this is not great news, right? But thanks to this compact property, -1 plus 1 to the power the whole ZD is also a compact space. And so those probability measures, they cannot go to infinity or anything. They cannot get mad. So at least it's very easy to say that you have substantial scaling limits. What is not easy is to prove that there is a limit. And the uniqueness of the limit is even more interesting and has to do with phase transition or not. Are there questions about the definition of the Ising model? Don't hesitate. Let me move to the XY model. So it's basically the same definition. I made this comment for a reason which will be clear in a second. The first small subtlety is that my state space, if lambda is still a finite box in ZD, the only difference is that S1 to the power lambda is no longer a discrete set. So to define a probability measure, I need to define a Radon-Nikodym derivative. So the way to do it is I will define d mu lambda beta xy against d lambda to the power, okay, maybe little lambda is not by d mu to the power lambda, where this is the uniform measure on the unit circle, tensor product, each vertex in my box lambda. So if you wish, this is the uniform measure on the state space S1 to the power lambda. So it's a very simple measure. Each point is sampled independently of the others, uniformly on the unit circle. And I want to define a probability measure which is absolutely continuous with respect to this one, and whose Radon-Nikodym derivative fills the energy of the configuration, will favor configurations that are aligned in a way which will be stronger and stronger as beta will go to infinity, or in other words, as the temperature will drop to 0. So this Radon-Nikodym derivative, in all of the talk, all of the lecture will be proportional to, and I will, in this case, tell you what that means also. Exponential beta, sum over the nearest neighbor vertices, sigma I, sigma j. So the first difference with the S1 model is that this doesn't have any meaning. So here I have the scalar product in R2. That's the proper way to generalize the Ising model in this case. And what do I mean by proportional to? I mean that this is a probability measure. I want this to be a probability measure. So I need to renormalize this so that it integrates to 1. So I will have 1 over a partition function of the xy model in this finite box at inverse temperature beta times this Boltzmann type weight exponential beta sigma I scalar product with sigma j. And this partition function, maybe I'm writing way too big. Is it good from the back to write big like that, or should I condense more?
Probably better than too small, right?
It's better than too small, yes. Okay, so here it will be a bit smaller. So the definition of this z, to make it 1, will be a multiple integral over S1 to the power lambda of these Gibbs weights, sum over I next to j sigma I scalar product sigma j, against which measure? Against this uniform measure on S1 to the power lambda. So d mu power all the site in lambda sigma. So this is the same as the Ising model, which was summing over the whole hypercube, except it's now integrating over the whole state space. So as in the xy model, as in the Ising model, the first remark also holds. So there are 2 equivalent definitions of xy model that are good to know. The first one, maybe let me say 2 equivalent definitions. So the second definition is to say that the Radon-Nikodym derivative of the xy measure in the box lambda at inverse temperature beta with respect to the uniform measure, let me just put d unif, at a configuration of spin sigma is proportional not to what I wrote here, but instead minus beta over 2, sum over the nearest neighbor sites, sigma I minus sigma j. And to generalize the Ising model, I have to take the L2 norm in R2 squared. So if I do this, the partition function will be slightly different. In fact, will be the same as this one up to a global constant, and the probability measure is exactly the same. So that's the second definition. A third useful definition that I will use a lot in the rest of this talk is to change the state space, to change the parameterization. Instead of looking at the unit circle to the power lambda, I will choose to look at it in terms of angles, so 0 to pi to the power lambda. So I just change the way of parameterizing points in the unit circle. And if I do this, so usually in my notation, a spin configuration will be called sigma in this space. And in the case of the xy model, a configuration, I will call it theta. And by theta, I will mean the collection of all the angles theta I, where I spans the box lambda. And in this third definition, what is the probability measure on this collection of angles? So maybe for pedagogical reason, let me take this small box of Z2. When I'm saying that I am summing over I next to J, what do I mean by that? I mean that the interaction is carried by the edges of my graph. So here the edges of ZD, while in Malin's lecture, the interaction is carried by the plaquettes of ZD, by the squares. And this third definition of the xy, each point carries a spin in S1, which I parameterize by the angle. So the angle here would be the theta I angle. And my pointy measure will be d pxy lambda beta. So maybe I shouldn't use the same notation, but I will. It's under a different. With respect to now the uniform measure, not on S1 to the power lambda, but on 0 to pi to the power lambda. At a configuration of angles parameterized by the size of lambda, I want this to be now proportional to exponential beta sum over all the ZD edges in my graph. And the interaction that I want to put here is the scalar product between theta I and theta j. And the scalar product in this case is cos theta I minus theta j. Okay? So I have three definitions, either sigma I scalar product sigma j, or minus 1/2 the L2 norm squared between sigma I and sigma j, or this cosine of the gradient of angles. They all give exactly the same pointy measures.
So couldn't you just write like sigma equals e to the I theta?
Yes, exactly. So the bijection here is that sigma as a field of S1 values is e to the I theta. So one is pushed forward of the other, everything is. So maybe before I get back to the slides, one can ask, what are the ground states? So the ground states in physics are the configuration with lowest possible energy. I didn't quite introduce the energy here. So in this setting, it would be the configuration with highest weight under those Boltzmann type measures. If I do the Ising case, then if I want to look for the configurations that have the highest probability to be picked, for example, in this definition, I want sigma I to be equal as much as possible to the neighbor sigma j, to make the exponential minus the highest possible. So in the Ising case, it's very easy to look at the ground states. There are only two of these. If I don't have boundary condition, it's either all pluses or all minuses. That's the ground states of my Ising model. If I do the XY model, I have more ground states. I have as many ground states as I have points in the unit circle. Right? The ground state is the set of ground states is homomorphic to S1. And each time I choose a direction in my unit circle, the ground state is made of everyone pick this direction and stick to it. And it's an easy exercise to show that if you take the new xy lambda beta, so this is the pointy measure on my state space, which is S1 to the power lambda, this converges in law, in distribution, as beta goes to infinity, to the uniform measure on this ground state, to the uniform measure on S1. So in other words, the zero temperature limit, the infinite inverse temperature limit, is a uniform measure on a very rigid configuration through the whole lambda box. Are there questions on the definition of the model? And then I will go back to the slides.
There was also something with ON. Could we also see it as ON valued?
Yes, so for ON, so yes, so I will make a comment. Since you said ON valued, I will take the opportunity to make two comments. So for the spin ON model, ON stands for the symmetry, not the target space, but I can also make a ON valued spin system, which in fact I will use later. So for the spin ON, my state space will be Sn minus 1 to the power lambda. The ON group is acting naturally on this state space. And each sigma which belongs to this, I will assign a weight. So if there is a Radon decoding derivative with respect to the uniform measure on these Sn minus 1 spheres. And the Radon decoding derivative is proportional. And you can pick any of the definitions you prefer. For example, exponential minus beta divided by 2, sum over I next to j, sigma I minus sigma j, and here it would be the L2 norm in R to the n. The Sn minus 1 sphere is naturally embedded in this square. And that would be the spin ON model. But I could also make a ON valued. So this is another example of a continuous spin system, which is natural. And would be a natural toy model for young males, a zero form instead of one form model like in Malin's course. But I could do a ON valued, or a SUN valued, or in fact a G valued, where this is any compact Lie group. And if I do this, if U is UX, UI, I in lambda, if that's a configuration, a field of group elements on my finite box inside ZD, I could define dp, so with values in the Lie group G, lambda, beta, with respect to the natural uniform measure, which puts an independent R valued, R measure, uniform measure on the Lie group at each point. And now this would be proportional, and one needs to find a good way to put the Lie group valued elements in the same direction. And one way to do it is to sum over I next to j. And I will use the group structure here. I can put ui star uj if it's a complex Lie group. And then the trace of this, and then the real part of that. It's a bit nasty, but... And I claim that the ground states of this interaction are as before. You pick one group element, and then you stick to it. All the others are pointing in the same direction of the Lie group. And this gives a Boltzmann type measure, which is Lie group valued. So this was both to answer your question and because I will need this in 1 hour or so.
Also, I'm now confused. And so the Lie group valued measure, even if we take ON, it's not going to be corresponding to any of this.
That's right. Except n equals 1, where U1 is S1. But then it's different.
Then what is the ON standing for then?
So the spin ON model is not ON valued, is Sn minus 1 valued, and the name comes from the fact that the ON group is acting on this. So if you fix any group element in ON, you can act on the state space by rotating simultaneously all the elements by this rotation. And unfortunately, I wasn't in Malin's course yesterday, but I guess in her course, the ground state is way more complicated than here, way larger. The ground state is made of all the zero forms. I don't know how Malin phrased it, but it's way bigger. That's why the model is more degenerate and very interesting. Are there, yes?
What is the sum explicitly in the Lie group case. What do you mean by neighboring elements?
Here,
Yes.
it's the same meaning as in the Ising, xy, or spin n. It means that I have my finite box in ZD. Maybe let me make it a little bit bigger. And what I mean here, my God, once was okay, but so it means each vertex here carries a group element. I don't want to draw a ON valued. Okay, let me say this is a matrix. And that's the point I in lambda, that's the point J in lambda. And the interaction is only summing over those edges of ZD.
Yeah, I got confused that summing in the Lie group, but not on the lattice. Yeah.
Yes.
It's
Okay, very good. No, but any confusion should be a question. Are you okay with the definitions? So in all those examples, we want to fix beta. The temperature is fixed. We want to fix the dimension, d. And then we want to let lambda grow to span the whole ZD and to ask ourselves, how do these measures look? What's going on? If I spot one spin, if I measure a spin somewhere, what does it tell me on the system very far from that measurement? Does the information flow to very far distances? Is there symmetry breaking, that's called this way? Or is it very noisy, very close to the uniform measure? That's the type of question we want to answer. So I will switch back to the slides, please. Yes, thank you. I'm really sorry, I didn't know. I was not able to do it myself. So, good. So, everything I did on the blackboard was there to justify a little bit what I meant by that, especially when the target space is continuous, because this is not quite accurate. I need to do Radon-Nikodym derivatives. Okay, so an important point is this beta, which is an inverse temperature. So keep in mind that beta large will mean that the probability measure will be concentrated on configurations that are more or less like that are very ordered. And beta small will be T very large, will be something very disordered. So the name inverse temperature is appropriately chosen, yet source of tons of confusion, so you can believe me. Okay? So here are some simulations. So that's a high temperature Ising model. They are stolen from the web. Maybe those are Vincent Beffara. This is a critical point, and this is a very low temperature, very large beta. So I think what has been done here is that the boundary has been set to be equal to plus. In reality, I think those are periodic, but let's claim this is plus boundary on the boundary. So this is breaking the symmetry. The probability measure is not invariant under sigma gives minus sigma, as it is the case here. All the probability measures I defined on the blackboard, if you act with the symmetry group, those probability measures are invariant under the action of those symmetry groups. If I now prescribe what the spins are on the boundary, this is breaking the symmetry. And the term symmetry breaking that you probably heard a lot from physics means that if you let lambda grow to the whole ZD, and you hope for a limiting measure in S1 to the power ZD, or G to the power ZD, or S2 to the power ZD, is it the case that this measure on the whole lattice remembers what you did on the boundary or not? If it does remember what you did on the boundary, it's called symmetry breaking. If it doesn't care what you did on the boundary, and there is just a unique possible infinite volume measure limit, then there is no symmetry breaking. So those three simulations tell you that maybe something was done on the boundary, but the system quickly forgot about it. And this configuration, if I put black to white and white to black, you wouldn't tell me something strange happened. It's very symmetric. This one is still symmetric, but it's non-trivial. It comes from the fact that the phase transition is continuous in dimension 2. And if I had found the same simulations in Z3, it would be a very important theorem by Eisenman, Duminil-Copin, and Sidoravicius from 2013, that at the critical temperature of Z3, the Ising model doesn't yet have symmetry breaking. And this is the high beta, the low temperature T, and this will remember the boundary condition at arbitrary distances. So, so this is I kept this information here because it makes a little bit of link with what Maurice talked about this morning, and probably, I'm guessing, what Antti talked about yesterday. I'm not fully sure. So about the two-point function. So in Antti and Maurice, I guess this one force, it's called the critical exponent, and it's heavily related to the delta exponent that they are telling you about. It's not the LQG1, it doesn't live on a random planar map, it lives on a Z2 map, but there is a KPZ relationship which relates both. So this one force is related to the delta of gamma equals square root of 3 to make a link. Another remark which maybe is useful, in those two courses you've been told all day long that the two-point function is trivial. The 3-point carries important, the structure function is for the 3-point, but the 2-point there's not much to do. This constant is interesting, it's the 2.1 on the lattice, but it's not universal, it fills the lattice. So there are many links with the two other courses, but you wouldn't see this constant in the LQG world, for example. This is lattice dependent, and this was found by Kaufman and Zager and also Young, so this is a link with Mylin's course. This has to do with, this is the same Young as Young-Mills. Maybe his work on Ising was important because 2 years later he did the work on Young-Mills with Mills. But, so this was just to make a small link.
What is the two times? What is the exact equal?
This?
Yeah.
This is equivalent in the sense of a series, like as y goes to infinity with respect to x, this divided by this goes to 1. So this is not the proportional of the Gibbs measure. This is really, this is more and more looking like that as x and y go far apart. So
1/4 is universal.
yes, this one is universal, and at the time was calculated using a transform matrices type of techniques and that exact diagonalization of those transform matrices. And later on, with conformal field theory, there was another viewpoint on this one force, which would be to compute it on the LQG side and use KPZ to guess the one force.
And the zeta, sorry?
This is the Riemann zeta. But it's lattice dependent, but it's beautiful.
Worse than epsilon function?
Not that I know of, but I've heard this morning that the gamma, I don't know. So before I go on, maybe let me show you some nice simulations that I often use that are due to Demidov, which are here. So this is a simulation of a 1000 by 1000 Ising model. And what's going on here is that there is a Markov chain. It's the easiest Markov chain you can think of, which locally resamples the plus and minus 1 bits. And this red scale on the right represents T, not beta. So this is very high temperature. And let me suddenly freeze the temperature. And so now the Markov chain is making best possible moves in some energy way. And we are now in the world of PDE, mix of PDE and probability. So it's very beautiful. There is some kind of median curvature flow, or something of that flavor. And I will tell nothing to you about this in this course, but this is still beautiful, and it would take a lot of time for the. So we see here that this is in a, I think, periodic boundary condition. And after a very long time, the system will decide whether it wants to be all pluses or all minuses, but this will take ages. And if I eat up a little bit the system, so we introduce randomness again. This is still PDE world, but a bit more randomness. And this middle point here is the critical point of Onsager. And here you see that the two faces are fighting against each other, but they draw very interesting lines. And it's an occasion to make another link with the last talk and Maurice's lectures as well. The interface between black and white, if I were to stop, because this is a bit shuffling too much, if I would draw the interface between the black and white here, this would be a very beautiful fractal curve, which is known to be the SLE3 curve. And this is a result by Shelkak and Smirnov from 2010 or so. Okay, so this is the Ising model. And on the same website, one has a simulation of the XY model. So here you have the 1000 by 1000 grid in Z2. So this is my lambda box at the beginning of this lecture. This is a finite big portion of Z2. Each point in this 1 million vertices carries a spin in S1. And this spin is colored in a periodic way according to its angle. If the temperature is high, so T is much larger than this bar here, it looks like an old-style television, the color one, and it's very noisy. It's almost a white noise. But if I were to zoom in, I think I can do that. Let me go a little bit closer to here. If I were to zoom in, I guess you don't see much, but one will see that it's not a white noise. There is still local correlation in this picture. But the way it evolves here is exponentially uncorrelated to the way it fluctuates at distance r. So there is exponential decay of correlation. And this is something very easy to prove if I'm far enough from this point here. So now if we go to smaller temperature, it will start looking like that. And we'll go back to it. This has to do with BKT, but I don't want to make a spoiler at this stage. Okay, so we'll see those pictures again, but I will stop. So maybe I will just make one last comment with the Ising model. I told you about the symmetry breaking. So how to another way to phrase this. Sorry, I'm bad with playing with this. There is this point here which is stop. Okay, I think what this button does, I think I could make it slower. Okay, believe me, what this point does is that if I press on cooled, this makes all the screen fully black, and then the Markov chain starts. So when I press on this, you see a bit of black. Do we see it? We see a bit of black, and then it gets quickly forgotten. It means the invariant measure doesn't care about the initial condition. You cannot break the symmetry with the initial condition. If I go to below the critical point, let's say here, and I make it all black, and I run the Markov chain, the theorem of symmetry breaking tells you that this will stay there almost forever. Not quite, because it's a finite Markov chain, so there is this Poincaré paradox, if you wish, that in a time which is proportional to exponential of the volume, maybe it will change its mind, but you will never see it. So here it will stay very stable, it will remember forever, almost forever, the initial state of the Markov chain, and this is another instance of symmetry breaking. Are there questions? Maybe a last thing I can say is that in physics they like to tell you about correlation lengths, and in some sense the correlation length in this picture would have to do with the highest island that we see in this random picture. Okay, so let me go back to the slides. So that was the simulation by Demidoff, and this was the way to periodically color the spins that are S1 values. So this was an instance of a high temperature XY model, and this is an instance of a low temperature XY model. And we can see some vortices. I will get back to those later in this talk. They are the engine behind the BKT phase transition, so they will play an important role. So what I want to tell you now is, for a while, I want to tell you that in dimension d is equal to 2, as long as you have a continuous symmetry spin system, there is no symmetry breaking. So it means if you try to break the symmetry either with the initial condition or with the boundary, when you will let the box go to infinity, the system in the bulk will forget the boundary condition. You will never be able to break the ON symmetry when n is 2, 3 or more. Only n equals 1, which is the discrete Ising symmetry, can be broken in dimension 2. And why that? So I realized I skipped one slide which was important, so sorry. Why is there a big distinction between discrete symmetry and continuous symmetry, at least in dimension 2? I want to tell you in a few words how symmetry breaking was proved in the literature for Ising model. I will not do it in details. You feel free to ask me at well, maybe tomorrow. Or at the coffee today. It's a 10 minutes argument, which I'm guessing most of you have seen, but if you didn't, this is an extremely beautiful and simple argument, which goes back to Peierls. And the idea to mathematically prove symmetry breaking is as follows. Imagine this is my n by n box in ZD, and imagine I break the symmetry on the boundary with plus, with blue in my picture here. To prove that there is symmetry breaking, one way to proceed is to ask yourself, what's the probability that a point in the bulk, for example, the middle point, but you could also pick this point here, what's the probability that this point changes its mind and has a minus spin on top of it? If you can prove that the probability that this point is minus is less than 1/3 uniformly in the size of the box, then you broke the symmetry. If this probability converges to 1/2, whatever you do on the boundary, then 1/2 is the symmetry case, and you didn't break the symmetry. So the game is to show that if beta is large enough, then this Bernoulli coin flip here is a biased Bernoulli coin flip uniformly in lambda, and uniformly far from the 1/2 Bernoulli coin flip. So let's ask ourselves what's the probability that this point is equal to minus. In order this point to be equal to minus, you need to have at least one interface gamma around it, which has plus outside and minus inside. It's not an if and only if, because if you have two such interfaces, you go from blue to red and back to blue. But as an upper bound, you can say that the probability to be minus is upper bounded by the probability that there exists at least one such interface gamma. And in probability, when we have probability that there exists something, we like to use union bound. So we can upper bound this by the sum over all those gamma of the probability that those specific gammas are a contour with plus outside and minus inside. And once you use the union bound, the only thing to do is for a given gamma to prove that it's exponentially unlikely in the length of gamma to find this precise contour in the system. And then Peierls' argument is a combinatorial argument which is counting those gamma, and there are exponentially many of those, but each of those costs an exponential cost, so if the rate of exponential is big enough, you win. So if you've never seen pairs, this is a disastrous way of saying it. But well, I can do it if you want. If there are, who has never seen pairs? Ah. Okay, so I know. I will make pairs for those who want after this is over, and we'll have 10 minutes less of coffee. Okay, so because pairs is very beautiful, but it doesn't work for continuous spin systems. Why? Because if you have a continuous spin system, then let's say you break the symmetry by setting all those spins to be east-oriented everywhere along the boundary. And say you want to show that the low of the spin in the middle is really far from the uniform measure, uniformly in the size of the system. If you could prove this, you would identify your symmetry breaking. So maybe you could say, I want to show that the spin in the... So let me make maybe a drawing. Imagine I want to do the pairs argument, which I will do during the coffee break. So I will go back to the slide in 2 minutes. So this would be a huge box in ZD. And maybe let me do the S2 valued case. Imagine I set all spin on the boundary to be north-oriented. So that's one way of breaking the ON symmetry. And by the time I reach the middle of the box, I want to ask myself, what's the probability that I end up in the south hemisphere, in Chile? So if this probability becomes 1/2 uniformly in the size of the system, it's a great sign that probably I did not manage to break the symmetry. So Fayol's argument, the point would be to show that this probability to reach the south hemisphere in the center is less than 1/3, let's say, uniformly in N, where N is lambda n is minus n to the power d inside ZD. What does not work in Fayol's argument is that the beginning of the argument is the same. In order to reach the south hemisphere, there must be an interface gamma or a surface in Z3, if D is equal to 3, where all the spins outside are in the north hemisphere, and all the spins inside gamma are in the south hemisphere. So this will still be correct. I will still be able to sum over all those surfaces or all those interfaces which have the property to have north outside, south hemisphere inside. What doesn't work anymore is that in the Ising case, if I have plus outside, minus inside, across the interface, there is a lot of energy which is lost. It's exponential minus beta divided by 2 times the gradient squared. So it's exponential minus beta divided by 2 times 2 squared. So each plus minus 1 along this interface is costing a huge number, and this number is too huge compared to the exponential rate of the number of such interfaces. If you are S1 valued or S2 valued, the danger is that it could be that those points are very close to the equator, so does those. And so the energy cost along the barrier is not so interesting. And you don't know if you're going to win or not against the entropy. So it would be extremely nice to have a pairs argument, but so far it's not known, and there are even arguments which suggest you cannot possibly find a pairs argument. So if you want to detect long-range order for continuous spin system, pairs argument is set to trash. You need something else, and in fact, in dimension d is equal to 2, where pairs argument works perfectly well, it's known that there is no long-range order. So that's what I want. So, sorry, just for one slide, it's hopefully designed for I'm sorry, I will try not to make so many back and forth in the next lecture. So in dimension 2, there is and I have to stop in 2 minutes. So in dimension 2, there is a theorem which is due to Mermin and Wagner. And this theorem goes back to the 60s. I don't know exactly which year. It first appeared for quantum spin systems, but I will state it for those classical spin systems. And it tells you that if d is equal to 2, then there is no symmetry breaking. And for continuous spin systems, for spin systems with continuous symmetry, let me write it like that. For spin systems whose symmetry group is continuous. So at least for the spin OM model, when n is equal to 2 or higher. And after the break, I will just give you the main ideas behind this proof. This proof is pretty old, but over the years, especially over the last 10 years, it became very popular again. And I will just give the main ideas. But the crucial idea is this picture, which is due to Berezinskii. This is called the spin wave. And what is drawn here is you set all the spins to be equal to east. And the middle one, you set it equal to west. And you ask yourself what's the best possible, the least energetic angle configuration which interpolates between the two. And what happens in dimension 2 is that you can find such a spin wave whose energy cost goes to 0 as the distance n, as the size of the box n goes to infinity. And the main idea in the proof is to look at the XY model, so the random one, and to perturb it very slowly with this spin wave in such a way that it's indistinguishable. So I will tell you what I mean by indistinguishable, but the existence of these spin waves prove that there is no symmetry breaking in dimension 2. And I will end the first lecture here by saying that for quite a few years, physicists thought that there is a mathematical theorem telling you there is no symmetry breaking. So for physicist eyes, it meant the model is completely boring, there is nothing to do here. And later on, in the 70s, they found that actually there is a transition, and it's a subtle one, and this will be the BKT transition. Okay, so unless there are questions, we can go to the coffee and I will do the payers. I would be very happy to be your first payers argument.